Dear students, in this video on atoms and nuclei, we will study hydrogen spectrum with some numerical problems. So let us begin with hydrogen spectrum. And see, in hydrogen atom, when electron jumps from higher energy level to a lower energy level, this energy difference is emitted as radiation. When electron jumps from higher energy state to lower energy state, the energy difference is emitted as radiation. This is frequency condition. You are familiar with it. And energy of electron in nth orbit is given by this relation. En is minus 13.6 upon n square electron volt. You are familiar with this equation. And now, using this equation only, you can see that the energy h nu, this radiated energy h nu will be equal to h, and frequency is c upon lambda, is equal to energy of initial stage, that is minus 13.6 upon ni square, minus energy of final state, minus 13.6 upon nf square electron volt. See, EI is for initial energy and EF is for final energy. So from here we can see that from this side, keep 1 upon lambda on left side, and on right side take this h and c to the right side. They will go in denominator. Then from here take this 13.6 outside, and inside bracket you will get 1 upon nf square minus 1 upon ni square. And then this constant, when taken in SI units, it is called R, Rydberg constant. And since it is 1 upon lambda, 1 upon wavelength, so the unit will be meter inverse, meter raised to the power minus 1. And this R is Rydberg constant. Its value is nearly 1.03 into 10 to the power 7 per meter. So we get a relation for wavelength emitted when electron transitions or moves from higher energy level to lower energy level in a hydrogen atom as 1 upon lambda is equal to R into 1 upon nf square minus 1 upon ni square per meter. Now, based on the final orbit, based on this final orbit, we have different series of these transition lines or these radiations. So, okay. So, when the final energy state is ground state, that means this is my final ground state is this one, and all the electrons are moving to ground state. Then the series of this spectrum is called Lehman series, and then this relation becomes 1 upon lambda is equal to R into 1 upon 1 square minus 1 upon ni square per meter, where this initial state ni can be 2, 3, 4 up to infinity. Then if the final state is first excitation state or n is equal to 2, then the series is called Balmer's series. And in this equation, now the value of nf will be 2. So 1 upon lambda is equal to R into 1 upon 2 square minus 1 upon ni square per meter, where ni is 3, 4 up to infinity. Next in line is Paschen series, when the final state of transition is second excitation state or n is equal to 3. or 1 upon lambda is r into 1 upon 3 square minus 1 upon ni square per meter, where ni is 4, 5 and up to infinity. Now this lies in infrared region. This Lehman series lies in UV region and Balmer series lies in visible region. So there is a sequence here. Ground state वाला UV region में जाएगा, first excitation वाला visible, beyond it Paschen series is infrared, then we have bracket and P fund also. So they all are in infrared region. So let us see graphically here how we see it. See, okay, so this is your E1 or minus ground state, and you know the energy of ground state is minus 13.6 electron volt. So if electron jumps from E2 to E1, E3 to E1, E4 to E1 up to E infinity to E1, then the range of radiations or range of waves which are emitted, that range is called Lehman series and it lies in ultraviolet region. And if the electron jumps to this first excitation state, which is E2, and its energy is minus 3.4 electron volt, first excitation state, and electrons are jumping from say E3 to E2, E4 to E2 up to E infinity to E2. Then the series that we get is called Balmer's series and it lies in visible region. Then if the final stage for electrons is E3 or second excitation state, the energy in second excitation state is minus 1.51 electron volt. Then you can see that electrons are jumping from E4 to E3, E5 to E3 up to E infinity to E3. Similarly, after this lies in infrared region. Similarly, we get bracket where the final transition takes place to third excitation state, that is minus 0.85 electron volt, and after that we have one more which is called P fund. They all lie in infrared region. And energy in infinity is 0 electron volt. When electron is in infinity state, that means it can leave the nucleus and move away from it. So its energy is 0 electron volt. And now from here we can see the same hydrogen spectrum but in a different form. So if this is your positive nucleus, this is the first orbit, n is equal to 1, second orbit n is equal to 2, third orbit n is equal to 3, fourth n is equal to 4, many more, and n is equal to infinity. So for Lehman series, transition takes place from n is equal to 2 to 1, 3 to 1 up to infinity to 1. Lehman series. Balmer series, the transitions are taking place to n is equal to 2. You can see this is n is equal to 2, you see. So transitions are taking n is equal to 2 and these lie in visible region. And one more interesting thing to notice, see the transition will take place from highest energy state infinity to the final state will have maximum energy difference or maximum frequency and minimum wavelength. So this can be violet and the minimum possibility of transition is this one. So transition from third to second, this will have minimum energy difference, minimum frequency and maximum wavelength. So this can be red color. Remaining lie in between. Let us look at Paschen series. So the Paschen series ends at third orbit. The principal quantum number is 3. See, these 1, 2, 3, 4 are their principal quantum numbers also. So this is Paschen series. This lies in infrared region. So similarly, we can have say bracket. So for bracket, you know that it will end at 4, and then 1 we have p fund also. So in this way you can understand hydrogen spectrum this way also. And then a very important outcome of Bohr's quantization condition, he could explain the de Broglie's theory. So de Broglie's explanation of Bohr's quantization condition. So let's see what it is. What he said, that when electrons are moving in their orbit, say this is nucleus, electrons are moving in their orbit, then they do not move like a particle. They move like waves, like particle waves. And these particle waves, they superimpose and form stationary waves. So only those orbits will be allowed where the circumference is multiple of the wavelength. So electrons in orbit form particle waves. They form standing waves in stable orbits. So for stable orbits, its circumference must be integral multiple of wavelength of particle. So now you can see that electron cannot be located as a particle. They will behave as waves in their orbits. So using this idea only, 2 pi r, the circumference, must be integral multiple of the wavelength lambda. So 2 pi r is in, see, lambda from de Broglie's hypothesis is h upon mv, h upon p. This is momentum. And from here, just change the sides. So take this mv to the left side, keep r here, and right side, take this 2 pi to the right side, and you get nh upon 2 pi. Now this mvr is angular momentum of electron. So angular momentum mvr is equal to nh upon 2 pi. So we can say that angular momentum of electron in stable orbit is integral multiple of h upon 2 pi. Now this is Bohr's quantization condition. So de Broglie's hypothesis explains Bohr's quantization condition. So the two theories are in agreement. Okay. So some numerical problem here. Find the maximum and minimum wavelengths in Balmer series. So for Balmer series, you can see the relation for this wavelength is 1 upon lambda is r into 1 upon 2 square minus 1 upon ni square per meter. And this initial energy state can be 3, 4 up to infinity. Now for maximum wavelength, this ni should be 3. See, for maximum wavelength, frequency should be minimum or energy difference should be minimum. And if energy difference is minimum, that means transition should be from the lowest possible energy state. So here n is taken as 3. So 1 upon lambda is r into 1 upon 2 square minus 1 upon 3 square. Simplify कर सकते हैं. You can take LCM here. And here, just take the reciprocal. And if r is taken as nearly equal to 10 to the power 7 per meter, then you get, this is nearly 7200 angstrom. So this will fall in your red region, red. For minimum wavelength, this energy difference E should be maximum. The frequency should be maximum. So here 1 upon lambda is 1 upon r upon 2 square, and for maximum energy difference, this initial energy should be infinity. Initial energy state should be infinity. So putting the value of ni as infinity, this term becomes 0, and just Simplify, you get r upon 4 and lambda minimum will be 4 upon r, that is nearly equal to 3600 angstrom, and this is going to be your violet color, right? So with this I come to the end of this video. I hope that it is useful to all of you. Thank you for watching it.